science session speaker, and it's Ariel Paul. Ariel is a research associate at the PhET Interactive Simulations Project. It's PhET, right?
It's
yeah.
PhET.
Okay. At the University of Colorado Boulder, where he works designing and studying interactive simulations for math and science education. Prior to joining PhET, he earned his PhD in experimental physics at CU Boulder in 2007, and then worked as a scientific instrument maker at GILA, which is a joint institute of CU Boulder and the National Institute of Standards and Technology. During his undergraduate, graduate, and subsequent work experience, he kept a constant interest in education, tutoring, and teaching at high school and college levels. So welcome, Ariel.
So this is science boot camp, right? So that means apparently I am one of your senior instructors, right? And I'm going to be asked, they came to me and said, actually, they came to a professor friend of mine and said, would you do this talk? And he conveniently was going to be out of town. So he said, hey, Ariel, would you mind covering, all of physics in 40 minutes? And I said, cool, let's do it. But that means I'm going to be asking some questions. I need you guys to just be Johnny or Jill on the spot with the answers, okay? If I ask you a question. So if it'll warm up. It'll be fine. So I like to start by saying, good afternoon, everybody.
Good afternoon.
Okay, that's good. So science librarians have a reputation, I think, for being in a quiet place. But today, you got to be a little louder, okay? So I entitled this From Stars to Spin, because we're going to cover the big portions of physics of the last 3,000 years in a couple slides, and then we're going to focus on quantum mechanics, because that's what John Bohn's mainly going to be talking about in his research, so we want to give you some background for that. So what is physics? Well, if we talk about the definition, well, science of nature. So yeah, we cover a lot in the topic of physics, and you can read for yourself the quote that's at least attributed to Richard Feynman. Yeah, it's like sex. It gives some practical results, but that's not why we do it. So I'm going to give us a functional definition for today. And the functional definition is going to be discovering and applying a model to some physical system, formalizing it in mathematics, and then using that to predict past and future behavior of that system. So let me ask a question. You got to answer quickly. Is this moving? No. Yes. There's a mixture, right? And so one thing I didn't say here is really to appropriate accuracy, right? Because I've been an experimental physicist. If I actually measured the motion of this, I could tell that it was actually vibrating at around 60 hertz because the mechanical fans and things in this building are vibrating 60 hertz. It's in a reference frame. The Earth is moving. Sure, it's moving, but for practical purposes, for what we want to say about it today, it's not moving. So that's the idea of modeling, right? I'm going to pick some simplification of the world. Sound good? Yeah. Okay. So I think it's appropriate to start with the stars, because that's really, for me, the beginning of physics. It's, to me, an absolute shame these days that most of us, how many people have seen the Milky Way with their naked eye? Okay, if you haven't, your homework assignment is to go out somewhere and see this. This is an inspiration for all of humankind, for all of history, for navigation, for figuring out the basics of geometry. And for the beginnings of physics, the huge bit was there was predictable motion in the night sky. We could see the fixed stars, and then there were these weird things. What were the weird things? The wanderers, the planets, right? Or things like comets. So there were heavenly bodies that we could predict the motion of, and we could understand what was going on, but maybe not the principles that drove their motion. But to me, this is the beginning of where physics starts. And so it's important, I think, to go out there, gaze at the night sky, because humans were able to do it for most of history, and it's only about the past 200 or 300 years that we haven't been able to do this. To me, a horrible tragedy. So that's where our story begins, with motion, what physicists call kinematics. And what's the first easiest model to think about? It's to think about particles as a point mass. So I can have complicated motion. This can rotate, but I can think about it just as a single particle at its center of mass. That's the easiest place to start. And most of us are familiar, even if we're not familiar with this equation, we're familiar with it. If I drive 60 miles an hour at a constant velocity for an hour, how far do I go? How about for 2 hours? Okay, that took Galileo to prove that if you move at a constant velocity and you double your speed, if you go for double the time, that you go double the distance, took him a 4-page proof, all geometry, because he did not have the power of algebra. You can prove that in 2 or 3 lines. It took Galileo quite a bit. But that is the first simplest equation we might come to in something like kinematics. I can start thinking about, well, what about if I can change my velocity? What about if I can move faster or slower in a different direction? I can add acceleration there. I can also think about situations where maybe I have some other kind of, we'll call it simple motion, like simple harmonic motion. I could talk about something oscillating, like a pendulum. And a lot of physics, the way we formalize a physical system is thinking about its motion, its position as a function of time, coming up with what we call an equation of motion. So we start with point masses, but all of these ideas for point masses we can extend. We can extend to extended objects, something like a basketball. Okay? Something like a basketball, if it's just stationary but rotating, those are all particles that are moving, single particles, but I can think of them as an extended body, apply those ideas to something like angular velocity or moment of inertia instead of mass. What causes motion? Well, one of the first ideas out there for causing motion was first with Aristotle had some ideas, right? Had thoughts about this. But then we moved on to a more formalized understanding with Newton. You know, this equation. That'll solve a lot of physics. In fact, a great physics professor of mine once said, you shouldn't be surprised that your intuition doesn't work when you get down to the level of quantum mechanics. You should be surprised that your intuition works pretty much on the level of everything you can see. From the smallest thing you can see with your naked eye to almost the largest thing. When NASA does their calculations to put people on the moon, they mainly use Newtonian mechanics. They're not using anything fancier for the most part. And so there, you know, the bane of introductory physics students, the free body diagram. But this also, Newton realized that if the way that I change something's motion is through forces, and the only way I can trade motion is through forces, then I must conserve this quantity called momentum. So for instance, if I drop this basketball and this ball, they'll accelerate at the same rate. But I may notice that the basketball, what's the difference between these two objects? Which one has more mass? Basketball. Same velocity, much more mass, and when momentum's conserved, I get some interesting results. What's the next big idea we came to? The next big idea, and this was a very difficult idea to figured out hundreds of years later, really fully after Newton, was this idea of conservation of energy, that there's this quantity, unlike momentum, that is conserved. And the reason it's so difficult is there's no direct energy meter. If anyone tries to sell you an energy meter, they're lying. Energy is always calculated. If I send this onto a photodetector, I detect a voltage, and I calculate what the energy of the beam is. Okay? So there's no direct energy meter. I can measure something's velocity, I can't measure its energy directly. And that's what made it so difficult. And energy for a closed system is constant and gets transferred between energy of some kind of motion and some kind of potential energy, right? So we have many kinds of forces out there that we can think of coming from fields. We talk about a gravitational field, an electric field, a magnetic field, the strong field, the weak field. And really when we're talking about potential energy, that is energy stored in a field. So when I lift this ball up, I'm storing energy in the gravitational field. Now this leads to a much different view of physics. Newton's view is the way a computer would solve things often. I feel some forces, I move over to this place. I feel some new forces, I accelerate to here. Feel some new forces, I move to here. The other view of physics, which actually the modern view, which John over there I'm sure uses a lot, is the Lagrangian view.
I'm using it now.
He's using it now. Well, he's sitting there, he's using it. Is this idea of minimizing action. Now, you don't need to know what action is, but let me give you some examples of what I mean by minimizing action. Okay? This is a classic problem. I want to move from this point to this point, and I have a ball that can roll on a track. What track shape do I use that gets the ball fastest from one point to a lower point? It turns out this is the path that's actually fastest. Because by dipping down a little bit below the point, I actually gain more speed. And it makes up for the fact that I've gone a slightly further distance because I can gain a little more speed from getting that gravitational field. Too low, not so good. Too high, not so good. Just right. Something else you might be familiar with is refraction of light. I go from something like air to glass, and I bend. One way to explain this is that I minimize the time it takes to do this. The classic example is, if this were a beach and this were water and someone's drowning here, I want to run longer on the beach than I swim in the water if I want to minimize the time that I get there. And that's some of the basics ideas behind the idea of minimizing action. But think, there's a totally different view of the world. That's like saying light understands that, oh, I'm going to run into glass. I can see what the entire potential field of the universe is, and I take the path that minimizes action. It's a very different view of the world. But interesting enough, comes to the exact same results as the Newtonian view. Mind blown yet? Okay, well, that's, a fair bit of physics right there. So if we put those ideas together, we come to a branch of physics called statistical mechanics, which is if I have all these little particles, like gas particles in this room bouncing around, they're going to follow these laws, but I can think about them as an ensemble. I can think about what are the probabilities that are involved in that, and probabilities become true laws when you do lots of coin flips, right? You flip a coin a couple of times, you may not get a 50-50 distribution. But in this room, there's something like Avogadro's number of particles, right? 10 to the 23rd, 10 to the 24th. If you're bored someday, flip a coin 10 to the 23rd times and see how your distributions are. They're almost exactly 50-50, certainly to any precision you can measure. And that's where we can get these ideas of things like the Boltzmann distribution. What are the speeds of the molecules in this room? How are they distributed at particular temperatures? Well, now we're in about 1860. And, well, I just had to throw a picture of Tesla up there chilling with some electricity, right? Because Tesla's awesome. So what are the basic ideas of electricity and magnetism? The basic ideas are we have these things called charges. Charges can put forces on each other. They create electric fields. Moving charges experience magnetic forces. Charges that are not moving do not experience magnetic forces. Electric current can create magnetic fields. Most of us, at some point or another, have wrapped a nail in wire, right, and made a little electromagnet. We've seen that currents can create magnetic fields. But interestingly enough, changing magnetic fields can create electric fields. There's a nice symmetry there. Oh, this is an extraordinarily powerful magnet. This is a piece of copper. It doesn't stick to the copper, right? It's easy. If I let this to a piece of iron, this is a 250 pound magnet, I work out, but I couldn't pull it off, okay? But what about if I do this? Can everyone see that? So what I have there is I have a changing magnetic field, right? This is a conductor. I have a changing magnetic field. And what that's doing is it's inducing an electric field in the copper, which is inducing a magnetic field, which resists this motion. Ever seen this before, Faraday's law? Awesome. One of the coolest demos you could ever do. And I'll let you guys come up and play with this afterwards if you're interested. But that helps to understand, what people did was they took these laws of electricity and magnetism, they solved them together, and they saw, that's interesting, I get a wave. I get the equation of a wave out of this. And that wave happens to be moving, when I solve for the units, at the speed of light. That's an interesting coincidence. So it turns out that light is an electromagnetic wave. And one of the ways to understand how it can propagate, a conceptual way to think about how can it propagate through nothingness? How can light propagate through vacuum? Because what do every other wave you're used to propagate in? Mediums, right? Water waves, sound waves propagate in the air. But light can propagate in a vacuum. And the way to think about that, one way to think about it is, I have an electric field that as it dies and changes, creates a magnetic field that grows. And as that dies and changes, it creates an electric field that grows, right? And so it's that self-propagating wave in nothingness. Well, light has been an extraordinary friend of the physicist. It's been one of the most powerful tools for discovering everything about quantum mechanics and the nature of matter. Okay? You all in your possession have a grating. Hold it up. John might not. Oh, they gave you one. Okay. let's be physicists for a second. Let's turn on this light bulb. Hold the grating to your eye and look at the light bulb. To your eye, what do you see? A rainbow, continuous spectrum, like at top. Okay? Now, let's turn that one off. Not so exciting. Maybe it's exciting to you, but let's let this turn on. Now look at that. Tell me what you see. Oh, that's what I want to hear. What do you see? Do you see a continuous spectrum? No. You see spectral lines. And in fact, think about the engineering that's gone into that. Someone has picked 5 lines, 5 colors that are spaced almost perfectly evenly, so it looks like white light to you, but it's not white light. It's not a continuous spectrum. And in fact, they've picked the brightness of them to be almost equal. And the brightness of them isn't actually equal. If I measured it, it's equal to your eye, because your color vision is sensitive at different wavelengths. Oh, I know. Well, I have a lot of physics to cover. I can't just stop. We're only in like 1890. We have all of quantum mechanics to go over. But this was hugely important, this discovery of spectroscopy. People really understood why. People were very good at spectroscopy. And they knew that if I took something like hydrogen or helium and just looked at the light coming from it, it had a very unique spectrum. It not only had an emission spectrum, so the gas was emitting light, but I could also shine white light on the gas and see where it absorbed light. And this gave us these ideas that atoms must be able to emit light and absorb light. And people had really gotten good at these spectra. And this has been really an amazing tool for discovery in physics, which we'll talk about more in a second. Now, at the end, near the end of the 1800s, physicists, because we're very arrogant, and we're like, we pretty much have it all figured out, right? I mean, think about it. They came from a place where there was darkness to where they now had electricity, right? And they felt like they really understood it. Classical electromagnetism is very well understood theory, and still much of the engineering done in the electrical world is done with classical electromagnetism. But there was a sticking point, as there always is in physics. There's this thing called the black body. Well, I'll call it the conundrum. It was referred to as the ultraviolet catastrophe. It was a catastrophe because we felt like we understood everything, but we totally blew the pooch on this one. Like, we didn't have it right. And the black body conundrum is this. If you take a box, you paint it all black on the inside, and you heat it up, and you drill a little hole in it, okay? You look at the light coming from that. I can do spectroscopy. I can look at the light coming from that. And the distribution looks like this. As I warm it up, it moves over to shorter and shorter wavelengths. Everyone's seen this. You heat up a piece of metal, it first glows sort of a dull cherry red, and it moves on in the spectrum after that. The temperature is indicative of the color. Okay? So it's coming from a black body. Now, classical physics would say this box is a certain size. Shorter wavelengths are smaller. I should be able to fit more in. And so what classical physics predicted is it said, look, this spectrum should go off to infinity. I should see an infinite amount of light in the ultraviolet. But I didn't. Okay? This was a huge sticking point, and it really upset physicists because they had this really well-developed theory. So how did we solve it? We do what physicists do. We answer the question, how, not why. That's what physics is about. Because you can always go deep enough and ask a question, why, where you don't have an answer. Why is there gravity? Well, it's curved space-time. Well, why is it curved space-time? I don't know. So, you can keep asking that question. So we answer the question, how? So that's what Planck did. He used this trick. He said, let me weight the energy of the different wavelengths by a constant. That's all he did. And my analogy for this is, let's say I give you a box filled with colored balls. Each of the colored balls are the same size, but they're different densities. Some are made of balsa wood, some are made of uranium. And I say, I want you to make that box 10 kilograms exactly. If we think about that spectrum, if we go back for a second and think about that spectrum, okay? If the colored balls that are ultraviolet are made of uranium, I can only put a few in there. And the reason is that the analogy I'm giving is if I want the box just to be 10 kilograms, this box can only hold so much energy. So what I need is the right distribution of balls such that some of them, a very few of them, are very dense. Some of them are kind of the middle density, and there's a tail end of small densities. And that's just the trick he used. He didn't know why, he just used a trick. Does that make sense? But that was a very powerful trick. It perfectly explained that spectrum. And moreover, it gave rise to these other ideas of quantization. So first came along Niels Bohr to help us understand the atom, right? In the atom, he said, well, maybe something else is quantized. Maybe the angular momentum, how the electrons move around the nucleus, is quantized. If that's the case, I can define specific orbitals, specific energy levels that the electrons can jump to. And this was highly successful at explaining the basic features, for instance, of the spectra of hydrogen. Did it almost exactly, except when people started to look a little more closely. Because that's what always happens in physics. You just go deeper down the rabbit hole, right? So again, quantization starts to come up. But there were some interesting questions. Well, why can I fit 2 electrons and only 2 electrons in that first orbital? Anyone heard of electron spin? I guess John has. We'll hope John has, or we're in big trouble. So electron spin is kind of an oddity, because it's not really, an electron's a point particle. It's not a charged ball that's spinning. It has intrinsic angular momentum, okay? And people are like, that's weird. Well, it's no weirder than something having mass, if you really think about it. It's no weirder than something having charge. It's a property. You could say, if it had color, which when you get into things, other kinds of physics, they call things having color, right? It's just a property. It's an intrinsic property of this, okay? It has this thing called spin. And there's something very interesting about spin. It only comes in a couple of varieties, half integer and integer. So that's like if there were 2 parts of the population. Parts of the population that only had half-dollar bills or half-dollar coins, and the other part only had dollar bills, right? That's basically it. And in that case, we can't trade them around, but if I have half integer, I can come in, $1.50, $2.50, negative 50 cents. And we call these 2 types of particles fermions and bosons, okay? Fermions have half integer spin. Those are things we're more familiar with. Things like electrons, protons, neutrons. And they follow what I like to call the urinal principle, or the Pauli exclusional principle. So if I have one guy standing here, I've been to this urinal in New Zealand. It's really cool, by the way. It's not a joke. It's a real urinal in a fancy New Zealand hotel. That is not me, though, as you can tell. So another man comes in. Which urinal do you think he goes to? The one next to me? Come on. Which one does he go to? The furthest one. These obey the urinal principle, right? They don't want to be the same. And I'll tell you this, I've been at a lot of urinals. I've had people come next to me. I've never had someone cross streams with me, okay? So in that case, what that tells us is this idea that for fermions with half integer spin, they obey what we call the Pauli exclusion principle. They can't be exactly the same quantum state. And what differentiates why I can get 2 electrons in there in that first energy level is one can be what we call spin up, one can be what we call spin down. Now there's another kind of particle out there. We said bosons.
Wait, I'm sorry. How can you not make a joke about a p orbital here?
You can see we have a nice physics department. So we have also bosons. I usually, when I teach, I call this the frat boy principle. If one's burning a couch, not so many do it. But if like 10 are burning a couch, they all join in, okay? But the nicer equivalent would be the wave at a football game. If just one person, one join, like, woo, not many people do it. But the more people that join in, the more want to do it. And look at this. It's a laser. It's all one color. It's all going in the same direction. It all has the same momentum. These are billions upon billions upon billions of photons, all with the same quantum state. So they're the exact opposite of fermions. They all want to sit more and more in the same state. And you're going to hear about Bose-Einstein condensates, right? So that comes from boson, or this guy Bose, who came up with these sorts of statistics. If you come up to any physicist on a dark alley and say, I want to sell you a wave, The physicist is only going to ask you one question. The physicist is going to say, does it interfere? Because to a physicist, that is the hallmark of a wave. That is what makes a wave a wave. Okay? And the way we initially showed this was with this thing called Young's double slit experiment, which is shown schematically there. You can do something very similar. If you take your two fingers, you put them together and make a tiny slit between them. And you put it close to your eye and you look up at the lights and squeeze that slit down, you'll start to see dark and light bands between your fingers. Can anyone see that? Some will, some won't. Try it later. It definitely works. You can prove light is a wave, right? That's how we prove it's a wave. It has destructive and constructive interference, right? Where peaks meet peaks, if I have two sources, this is a picture of a water wave. If I have two sources where I'm making ripples in the water, where peaks meet peaks, they add up together. Where peaks meet troughs, they cancel each other. And in between, we get a mixture. Shall we show off some interference? Yeah. Okay, let's do a Young's double slit experiment right here. Let's see if we can do this without blinding anyone. That'd be positive, including myself. Can everyone see that? Can everyone see that? Okay, so these are double slits. Let me see if I can do this. Ooh. So that's a green laser. And what I can do is I can change the slit width. I can do all kinds of fun stuff. I can also take the gratings that you have. And if I take multiple gratings, oh boy, I can get neat patterns with multiple gratings. And in fact, you guys ever heard of X-ray crystallography? Yeah. So X-ray crystallography works on exactly this principle. We bounce light off of crystal structures. It diffracts. We look at the diffraction pattern and we can reconstruct what the pattern is. That pattern is very simple. It's just a bunch of lines. So, interference, a key part of knowing if you're a wave. Well, at the time that people were discovering these ideas in quantum mechanics, came along Mr. de Broglie, who wrote a 5-page thesis, PhD thesis. That'd be nice, right? And apparently, logic was very prime in France at the time. You know, this is after, the heritage of people like Descartes. And my physics professor once said he had a friend who was in France at this time who had a baby. They were American. They had a baby in a pram, and they had this very soft pillow. And this French woman came over and said, "You can't put a baby on this soft pillow. They'll suffocate." And she said, "Well, we all do this in America." And she said, "Well, they will all suffocate then." So their logic was very much in the minds of the French at the time, okay? So what de Broglie said, he said, well, it seems like light, initially we thought it had a particle nature, but we see it has a wave nature. Matter has a particle nature. Maybe it has a wave nature. And in fact, once people looked into it, they saw, hey, I can do the same double slit experiment with electrons. And I don't just get two streams of electrons on my screen, I get an interference pattern. To a physicist, if it interferes, it's a wave, okay? So that brought up a lot of very interesting questions when people saw this. What is waving? What is the thing that is waving, okay? And hopefully we'll have another mind-blowing moment here. What's waving is what we call a probability amplitude, which may not mean much to you, okay? But the light in this room is more or less unpolarized. Okay? These are polarizing filters. Okay? You'll notice if you look at me through this one, I look a little dark, right? And the reason is that we could think about the light in this room having equal probabilities, any photon even of light having equal probabilities of being polarized with respect to the filter or opposite the filter. So I block out about half the light. So no light, or sorry, light coming through pretty easily, and I cross these, right? I've made a measurement. I've done what I call collapsing the wave function. I've taken all of these, all the light that's coming through here should basically be polarized in one direction. I put a polarizer that's 90 degrees to that, I get no light through. Let's see that on the board with a laser. All right, this is going to be tricky. John, can I have your help? Can you point the laser away from your eyes and towards that screen.
Let's find out.
It comes out this end.
Is there,
I'm going to turn it on.
is there a button?
Yeah, I'm going to turn it on. Yeah, okay.
Is that good?
Yeah, that should work. That should work. So what I'm going to do is I have my two polarizers. I put one in front of it, and you'll see, obviously, it's less bright. I can cross the other one, right? And I can basically extinguish a lot of the light. Now let's see what happens. So I've got them crossed right now. Oop. If I put one in at 45 degrees, see what happened? It gets brighter. Can you see that? You're seeing quantum mechanics, collapsing wave function in action, right? And let me explain that. We can turn that off. There. Somewhere. Yeah, boom. Isn't that weird? You insert something. You put more stuff in the way. It gets brighter. How does the light know? Right? And the thing is, when we talk about linear polarization, well, what's up and what's down? What's side to side? It doesn't mean anything until I do this. I make a measurement of the state. Well, now, if this is basically making a measurement of the state, the light is polarized, let's say, vertically. If I put it through this filter, well, that's opposite. It's orthogonal or perpendicular to it. Cross it out. But I've put one at 45. Now I've changed the meaning of up and down and side to side. Quantum mechanics, what?
There are 3 pieces of
Yep. There are 3 pieces of film. You can do this if you have sunglasses. Polarized sunglasses, grab 3 of them, shoot a laser through it. Seriously, take any polarized sunglasses, cross them. You'll see them dark, shoot a laser through it. Try to get a third one in at 45. You'll see more light come through. Very strange, but that's quantum mechanics. We don't care why, we just care how. All right, this is going to be a fun one to try to explain, but I'm going to give it my best shot. Any of you heard of the uncertainty principle? Okay, anyone here a singer? You got to tell me if you are. Sing a C note for me, please. Just, you can fake it, I won't know. Oh, it's beautiful. Okay, so what happened there? She kind of built up, then she sang a C note, okay? If she instead had sang a C note, let's in our minds imagine a C note that went on for infinity, okay? Forever in time. A C note that went on for forever in time, if I plotted its frequency versus its intensity, would be very peaked. It would be one frequency. It would be very easy to know. But look, when she sang, this is classical uncertainty, not quantum mechanical, just classical waves. When she sang, it kind of built up. I got a wave, and then it fell back down. If I graph this in frequency, most of the frequency would be back at that C note. But there'd be some other weird contributions from down at these tail ends, okay? And in fact, any funky waveform I get, I can think about it in what we call frequency space. So for instance, if I do this, clap. When I clap, that's very peaked in what? Time or frequency? Time. It's very peaked in time. And that actually means it's going to be very spread out in frequency, because there are going to be a lot of frequencies in there to build up that wave to look like, because what's that wave going to look like in time? That wave is going to look like this. But in frequency, it's going to be all spread out. Maybe you ever wondered, why does a C note sound different on a piano than a guitar? They're both C notes, because they have different frequencies in there. The fundamental frequency is a C note, but there are different harmonics of the instrument, right? And this is the idea of uncertainty. The analogy being position and momentum are a lot like this, okay? If I'm peaked in position, I need to be spread out in momentum. If I'm peaked in momentum, or I know my momentum well, I need to be spread out in position. All of this knowledge that we've collected about physics, and particularly this idea of spectroscopy, so let's relate it back. Does everyone know their stardust? You better. It's important. Every single element above lithium has to be baked in the center of stars, okay? If you're in a star, the way a star works is through fusion. I build up all of these elements in the star. Some stars aren't big enough. They just make it to iron, and then the star dies. Sits out there, just a big chunk of iron. But some that are more massive, they collapse further. and they form a neutron star, all just neutrons. Why can't the neutrons push into each other further? Because of the Pauli exclusion principle. So they get stuck there. But if you're really massive, you even collapse further than that, and you explode in a supernova. And you release all these other elements. So that means that at some point, all the carbon in your body was in the center of a star. And I think it's a beautiful thought to think that really you are the universe looking back at itself. That written into your very DNA is the desire to try to understand yourself. And the reason we know this is by looking out at other stars and seeing they have the same spectral lines. We can tell the same elements are in there. And by using all of our techniques that we have of modern physics to tell what's a very beautiful story, which is much deeper than this. So that's pretty much all of physics. In more or less, was I on time?
Yeah, you're doing good.
Okay. And so I believe I have time for questions.
If you lighten the mass, whether through ocean evaporation or internal liquids coming out, what happens?
There's a lot of interesting things. It's not so easy to lighten the mass of the Earth. The main thing that lightens the mass of the Earth at the moment is helium is a non-renewable resource and comes out of the ground and does actually leave our atmosphere. But it's a very small effect. But you could imagine that would have amazing effects, right? You change the moment of inertia of the Earth. You change how fast it spins. You change the gravitational force between it and the other planets. I mean, there are a lot of effects that would happen if you change the mass of the Earth. In fact, you can actually see, because we've pumped water to different places because we have reservoirs everywhere, we have slightly, measurably changed the moment of inertia of the Earth, and you can actually see that its rotation rate has changed. People have measured that. It's a subtle effect, but it's measurable.
Where's Einstein's E equals mc squared fit into this?
Oh, sorry, I didn't cover special relativity. I can cover that in about 2 minutes if you want me to. Okay, so yes, special relativity. So we can cover special relativity in maybe 2 or 3 minutes. We'll give me 3 minutes. So special relativity, the idea was that people were saying, what's this medium? Everyone was used to a medium that something traveled in. So people came up with this idea of ether. And people had all these fancy experiments to see, if I send light one direction and measure its speed and send it the other, is the speed slightly different because the ether's moving and all these questions. And so Einstein came along and said something different. He said, let's do a simple experiment in our minds. Let's pretend the speed of light is constant for all observers. Okay? If the speed of light is constant for all observers, let's make a simple clock. Okay? The clock is this. It's a laser bouncing back and forth between two mirrors. Okay? And so a tick of the clock is dink dink. Okay? Now, what happens if I see this clock on a spaceship moving quickly by me, right? Right now, you see this ball just going up and down in my hand. If I were in the back of a pickup truck doing this, the ball would still be going up and down to me, but to you it would look like this if the pickup truck were moving. Because you'd see it moving through space at the same time. So what you would see this light doing is this. Okay? And what that tells you is something interesting. If the speed of light is constant, I'm still going to measure the same speed of light. But is this light traversed a bigger, smaller, or the same distance than this light? I'm going to go with bigger. Right? This is the same. So this is the hypotenuse of a triangle, right? It's longer than one of the sides. Okay? So it's traversed more distance. More distance, same speed. What has to happen to the time? The time actually has to get longer. This is the idea of time dilation. That's all. That's special relativity. Einstein said, here's a postulate. Speed of light is constant. What are the wacky consequences of that one? And then you go out and measure it. And that's the true predictive power. When you have a really powerful theory, you come up with something like this and people go, no way. Then you measure it, and when you get the right answer, people start to think, maybe that theory has some validity to it. So, this has other strange consequences, of course, but length contraction and time dilation are two of the big ones. But that, to me, is the easiest example to see what are the weird consequences if you say the speed of light is constant. And that's, I think, an easy place to see it. That was Einstein's, one of his first thought experiments for that idea. Any other physics I didn't cover? Did that answer your question?
I'll throw out another one.
When did quantum entanglement come about?
Oh, so this is the Einstein-Rosen-Podolsky? Is that? Yeah, that's fine. I'm going to let John field that one. I think it came about in the 60s, or maybe the 40s was first thought about.
55.
Okay.
Before that. I don't know what it was, 30s or 40s.
That's when they first started to think about the odd ideas, but really being able to see it and measure it is sort of in the late 90s, is that right?
No. Aspey did this experiment probably in the 70s.
See, you're asking the wrong person on quantum mechanics, but I have my reference librarian right there.
What are some of the big research questions that are active right now in physics?
The big active questions. Is that what you said?
Big research questions.
Big research questions. There are a lot of big research questions, but I think certainly one of the biggest ones is we always say there are these little, sores in the roof of the mouth of physics. And I'd say the biggest one these days that a lot of people, certainly in cosmology, are interested in is, for a long time it was understood that the universe was expanding. Hubble did this work. And how did he do it? Through spectroscopy. He saw that there's this thing called the Doppler shift, right? We looked at spectra and we said, well, that looks like helium, but it's moved over a little. And that's because light Doppler shifts. You're familiar with Doppler shift when a race car goes by. The sound you hear is, right? It's got a different pitch to it if it's moving than if it's just sitting there running, right? And light's the same way. If something's moving away from me, the frequencies get shifted when I look at them. So we're able to measure how the universe is expanding through spectroscopy. It's also one of the ways we're able to find planets, is to look at stars and we can see them oscillating in their spectra. So as I mentioned, spectroscopy, a very powerful tool. But not only is the universe expanding, it's accelerating its expansion. That's weird. And no one understands that. There are these theories about dark energy, and no one's really sure why. So that, I think, if you're looking for sort of the next testable frontier of physics, that's one that's very interesting and people have no clue about. And one of the things you need to understand that I didn't make perfectly clear, probably, physics is always an effective theory. For every length and energy scale, you can find a theory that works well. Newtonian mechanics works well when designing a car. I don't usually worry about quantum mechanics unless I'm designing transistors, or I do what John does. So for a lot of things, you don't need it. But when you go to very big lengths, very big energies, big masses, small lengths, small masses, things get weird. And the further you go, you'll always find new physics, because every physics theory is an effective theory.
Bohn from the University of Oregon, and it is my great pleasure to introduce Dr. John Bohn. Dr. Bohn is a research professor at CU Boulder and a fellow at JILA. JILA was formerly known as the Joint Institute for Lab Astrophysics, and it is jointly operated by the University of Colorado and NIST. Research at JILA includes astrophysics, atomic and molecular physics, and optical physics. Dr. Bohn's research focuses on quantum mechanics as it relates to the behavior of gaseous matter at temperatures just above absolute zero. And here is an interesting tidbit about Dr. Bohn that librarians will appreciate. His paper, Prospects for Bose-Einstein Condensation in Ultracold Molecules, which was published in Laser Physics in 2003, is in a tie. It's in a 30,966 way tie for the least cited physics paper.
Take that, Fermi. Well, thank you very much. It's a pleasure to come here. It's a pleasure to invite you to our university. I apologize for all the construction going on. You probably cannot get anywhere that you're going on this campus. And it's also going to be a pleasure to talk about some, let's say, more contemporary aspects of physics, the things that we think about in quantum mechanics these days now, over at JELA and elsewhere, lots and lots of laboratories around the world. I want to thank Ariel for giving me a beautiful, spectacular introduction to physics that will set things up here. Who am I kidding? I can't follow and act like that. He was really something. So let's get to it. I'm an atomic physicist dealing in the physics of atoms, and right away alarm bells go off, because if you think about the history of atomic physics, which Ariel kind of hinted at, it was a cutting-edge research topic, absolutely the most important thing in physics in about 1920, right? Back then, you did not know how an atom worked. Let's jump ahead to the slide here. So in about 1925, when quantum mechanics was invented, to understand how atoms worked required a completely new understanding of how things behave in the universe. Quantum mechanics was invented, and it was such a fertile period in those days. Within a year or two, the basic properties of atoms had been completely laid out. Molecules, at least the fundamentals, were understood. Solid state physics, things made of atoms like this table, the basics were laid out for you. And maybe that was it for atoms. And you could start to say, well, you know, inside the atom, you know, we understand atoms, and in a sense, mainstream physics left that behind and said, let's look inside the atom. Deep inside, there's a nucleus in the atom. Inside the nucleus, there are protons and there are neutrons. And if you look hard enough, inside the protons and neutrons, there's other stuff. And there was all this hoo-ha about elementary particles and atom smashers and creating new particles and electroweak physics, whatever that means. And there's a sense, and I think it's a sense that's very prevalent in popular appreciation of physics, that that's the fundamental physics. That's where physics is going. You're looking into the mind of God, right, to quote books that you've heard about. And it culminates in sort of the Higgs boson. And there's a sense in which atomic physics was left behind. The rest was just to work out the details, to do the stamp collecting part of atomic physics. And it's very important because it's kind of a service industry. You need to know about properties of atoms for things like chemistry or astrophysics or plasma physics, and there's nothing wrong with that, but maybe the fundamental discoveries were gone. In 1960, the laser was invented, and we had suddenly much better control over light than we would have had from, say, an incandescent light source. And that, again, sort of changed everything. You could look at atoms, as Ariel indicated. Spectroscopy was great in those days and still is. You can look at atoms in much more detail than you ever could before, but it was still sort of its own field plodding along, looking at more details of more atoms. The big break happened in about 1990 or thereabouts, when it was understood that you could use the lasers to push the atoms around, to control what the atoms were doing, to start engineering matter at the atomic scale. And that's the development that is still going on today. It is, I would say, poised for a big, big breakthrough right about now. Since that time, we've been learning more and more about how to manipulate atoms. And the subject today is going to be about why we're manipulating atoms in this way, what we hope to come out of it, or at least an overview of that. And just to give away the secret, it's one thing to understand the quantum mechanics of a single atom, and if you can control it, to worry about its quantum mechanics as it moves around. The real thing now is, what if you had lots of atoms together at once, and they're pushing on each other, and they're doing stuff to each other, and it gets to be a more complicated system. It is a very hard thing to understand, especially if quantum mechanics is involved. If you want to think about it, we're studying quantum complexity, and we're trying to do quantum complexity from a simple point of view, and the atoms make it simple. That's the story I'm going to be telling. All right, and to do this, we're going to go to the ultra-cold limit, and I'll tell you by and by what I mean by ultra-cold. But in broad strokes, you think about the history of science, and again, Ariel set this up wonderfully. If you build a better telescope with a bigger mirror and you can see further out into space, you learn something. If you build a better microscope and you can see smaller things, you learn something. And if you go to higher energies, high temperatures, there are interesting new phenomena. Really high temperatures. If you go to low temperatures, there are other interesting phenomena. Anytime you push the limits of your measurement technology, you learn something new. That was one of the original motivations to go to ultracold. So let's talk about temperature. How cold is ultracold? What I've drawn here is a kind of schematic thermometer here. It's marked off in degrees Kelvin. That is basically degrees Celsius, but measured where 0 is at absolute 0, the coldest temperature you can conceive of. And it's a weird thermometer. It's not marked out. Each mark is not 1 Kelvin, above the others. Each mark is a factor of 10 above the previous mark. So here's 1 Kelvin here. There's 10 Kelvin, 100 Kelvin, 10 to the third is 1,000 Kelvin, and so on. Down below that, there's a tenth of a Kelvin, a hundredth of a Kelvin, a millikelvin down here, and on down here. On this scale, absolute zero would be infinitely far down at the bottom there. Absolute zero is kind of hard to really get to, but we're going to get much colder than you might think. Just to set things in context, there are some phenomena in the universe that have sort of characteristic temperatures. The temperature of stars tends to be in the thousands of Kelvin, way up at the top of our scale here. The temperature of almost everything we know and interact with on a daily basis is in the hundreds of Kelvin. Even things that you think of as cold are still hundreds of Kelvin, right? Blistering hot from my standpoint. Whoops. The coldest temperature you would find in nature is the temperature of outer space itself. Obviously inside here it's warmer, but out here the temperature of space is about 3 Kelvin. And if you want to go colder than that, you have to do it in a laboratory. You artificially make temperatures lower. And here's one gimmick for it, and we'll just call this sort of very cold indeed. There are special refrigerators. There's one picture here. This is actually on campus here at Jella, where the refrigerant is not, I don't know, do they still use Freon? Probably not. Whatever it is in your refrigerator is some kind of coolant. Here they use liquid helium because it has special properties, lets you to go to low temperatures. And they get to temperatures of maybe millikelvin. And interesting new phenomena appear there. What I'm talking about today, have I built enough suspense here? How about now? Okay. We're going to go down here, and I'm going to schematize these ultra-cold gases by atoms in a bottle, because they're held in some way. And we're talking now about 10 to the minus 7 Kelvin. Let's count the zeros, shall we? 1, 2, 3, 4, 5, 6, 7. This is 100 nanokelvin, where nano means 10 to the minus 9, a billionth of a Kelvin. That's the kind of temperature that can be produced in the laboratory in a gas of atoms. And that's where we'll spend most of our time here. But to motivate this, there are some very interesting phenomena that happen up here at sort of Kelvinish temperatures, and they help set the context. One is superfluid helium. That is, if you take liquid helium and cool it down below about 2 degrees Kelvin, it has this weird property. And to illustrate the weird property, I'll contrast it to water. If you take a bucket of water and you start it spinning, you put your finger in it and you spin it around like this, you can see the vortex in there that forms, or maybe there's water going down the drain or whatever. And then when you stop spinning it and take your finger out, pretty soon this vortex winds down to nothing because there's viscosity, there's friction of the water against itself, and it dissipates the energy all over the place, and pretty soon you're back to still water again. Not so in superfluid helium. If you take a bucket of superfluid helium and stir it up, you don't use your finger, but whatever you do, you stir it up and you let it go, it just keeps spinning. It goes and goes and goes. This is a kind of strange picture from the University of Maryland. They're hard to image, these little vortices, but each dot here is basically a picture looking down the top of one of these vortices, and they start these up spinning, and they last for hours or days or however long they have to do the experiment, or until something else goes wrong and destroys it. They are fluids that have no viscosity, but they have to go to low temperature to see it, and it's a quantum mechanical thing and a fantastic phenomenon. Another one that you've probably heard of is superconductors, which is a similar thing. You know what a conductor is. It's a piece of metal, like the slab of copper we had out here. And conduct means conduct electricity. And electricity means you put voltage across this wire, and the wire is made of copper, and the electrons go from one end of the wire down to the other end, and that's the current flowing. And your picture of it might be, well, the electron just hops into the wire and smooth sailing all the way down the wire. But no, it's not so. In an ordinary wire, there's atoms. The wire is made of atoms, and the electron goes bonk, 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 rattles off of all the atoms there. Every time it hits an atom, it heats things up. And so ordinarily, when you conduct electricity through a wire, you heat up the wire, you're losing energy. You have to maintain that voltage to keep a current flowing. But in a superconductor, you don't. Again, if you go to a low enough temperature, maybe a Kelvin, or it depends on what it is you're looking at, the electron flies right through as if it's not bouncing off the atoms. How does it do it? It's a quantum mechanical thing, because it's not like a particle going bonk, 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 bonk against the atoms. It's like a wave, and the wave can slide through the atoms somehow. And I'm not going to get into a lot of detail about that, but that's the idea. It's a quantum mechanical thing. And it raises an issue. How come it's 1 Kelvin or so for, say, a block of aluminum to go superconducting? And the answer is, well, in about the 1980s, people found there are other materials that they could mix up in the laboratory, and those would become superconductors at much higher temperatures, 50 or 100 Kelvin. And that's wonderful, because if you could make a transmission line out of a material that was superconducting at, say, room temperature, 300 Kelvin, you could transmit electricity without losing any power at all. It would actually be a tremendous gain, but nobody knows how to do it. It's a black art how to make those things work. Well, that's saying too much. It's alchemy. And the problem is because it's so very complicated. So these phenomena are low temperature phenomena. This sort of flow without resistance is a low temperature phenomenon. It's very much quantum mechanical, but the details are very hard to work out, and here's why. If I look at superfluid helium, here's a little bucket of superfluid helium, and I take a microscopic image inside there somewhere, and I look. Superfluid helium is a liquid. What's a liquid? Well, in a liquid, the atoms are pretty much free to move around, but they're packed in shoulder to shoulder, and they're bonking into each other all the time. And if I want to understand how superfluid helium works at a deep, detailed level, I want to know how this atom moves. Well, let's see. That's obviously affected by how this one moves, because it's banging into that. It's obviously affected by this one. But wait a minute. This one's affected by this one, and this one. This one's affected by this. And they're all together. They're all affecting each other at the same time. And a truly microscopic description of this, you would want to follow the motion of every particle or every wave, which makes it even harder, right? And there's too much going on to follow in a lot of detail. Here's an analogy. We say that the atoms are correlated. And here's an analogy that does not involve quantum mechanics. It's a very classical system, the game of Jenga. And here's an example. You know this. You have these rectangular blocks, and you stack them up in a tower like this. And the game consists of, I try to remove a block, but, I can't take the block off the top. That would be cheating. I actually don't know. What are the rules of that? How do you decide which block to take?
Yeah, I don't think.
Because that would be a pretty stupid game if you just. But you don't. You don't, obviously. You try to take the blocks out of here, and you try to make your opponent take the blocks. The point is, I'm off top. The point is, if I look at one block and I say I'm going to pull this block out, that's a pretty simple thing to describe, a block moving on a line, right? That's completely trivial, except the motion of the other blocks can depend on that. If I take this block out and these start to teeter, then these depend on this one moving, and there they go, and then these depend on those, and these depend. It's correlated, you see. If you want a description, you'd have to describe them all at once. And I'm oversimplifying. There are good ways, like statistical mechanics, to describe them all at once, but there are details that are hard. Here's the same kind of point of view, but looked at for the superconductor. What is a superconductor? Well, it's made up of a bunch of atoms. Here they are. This is an artist's rendition of the atoms inside a certain type of superconductor that carries electricity without resistance at temperatures of whatever, 40 degrees Kelvin. I don't know which one this is. Each of the circles here represents an atom, and the different colors are different kinds of atoms, and so there's some kind of very elaborate arrangement of atoms in this thing. And this whole pattern here is repeated over and over and over again, and over and over and over again to make a chunk of this stuff. And you ask yourself, what do we know about how electrons move through this stuff? Here's an electron trying to move through. Well, the first thing I can see is it's not obvious, right? The electron, which moreover is some kind of a wave, has to move through all this stuff. The wave is scattering off of these and diffracting and interfering through this incredibly complicated pattern of stuff here. So 1, you have to know the pattern of stuff. 2, you have to know how the electron goes through it. 3, I didn't tell you this, but the electrons are fermions. What's a fermion?
Urinal.
Bunch of guys at the urinal. Right? Fermions by themselves don't act like superfluid, don't act as superconductors. First, you have to get the fermions to come together. 2 of them come together to make a boson. The boson can travel without resistance. How do they come together? Because they're doing something in the way they see the atoms. It's a very complicated mess, and I don't want to go too much into it, just to emphasize how complicated it is. Moreover, this is just something you mix up in a bucket in a laboratory somewhere. There could be mistakes in it. One of these green atoms could be just missing somewhere, and that makes things rotten for you. Right? So it's too hard to understand this, and because of this, It's not like somebody can sit down and say, today I will design a material that is superconducting at 200 degrees Kelvin. You just can't do it. 30 years we've been at this, and physics does not know enough to deal with this problem. You want to look at something simpler. And that's where the cold atoms come in. The cold atoms can be simple or complicated, but the point is you're under complete control over that. That's the story I want to tell. So what about ultracold atoms? One thing you should know is that, I forget if you touched on this, but quantum mechanics is something you see if you look at things that are really, really small, like electrons. Atoms are really, really small, except they're much bigger than electrons. Right? And so for a lot of purposes, like if I were going to talk about the molecules in the air of this room here, I don't need quantum mechanics to think about that. But if I have them moving really slowly, that's the other ingredient. Slow moving things, that is low temperatures, will put me in the quantum mechanical regime. So cold enough atoms behave as quantum mechanical entities. That's good. The other thing that's really going to whet our appetite here is that these are gases. These are dilute gases. If I make an ultra-cold gas, and it's in some kind of bottle like this, it's not like the atoms are all crowded up together and pushing all on each other at the same time. It's more like they're pretty much separated atoms and they're all doing their own thing, and then maybe once in a while, they probably don't spiral like this, but it's, but you know, I've got that vibe now. And once in a while, yeah, maybe they come together and they bounce off each other, and then they, you know, hi, how's it going? And then off they go. But the point is, to understand this, I can understand them maybe even at the level of one atom at a time, rather than all of them. Maybe two, because they run into each other. Maybe three, okay. So it's much simpler. That's the main thing that makes it simpler than understanding superfluid helium. And now, right at this point, you object. You're sitting there thinking, this is absolutely insane. You're telling me that the coldest thing in the universe is a gas? What? What the what? Because I know if you take a gas and cool it down, it turns into a liquid, right? A liquid turns into a solid. How can the coldest thing in the universe be a gas? And again, it goes back to this fact that it's so dilute. I start with a gas that is incredibly, I will bring it up later, but it's a million times less dense than air, right? If I cool it down, yeah, actually it will eventually coalesce into a solid, but it takes time to do that. It's so dilute. How does it clump into a solid? Well, you know, 2 things have to come together, then 3 things have to come together, and 4 things. And while you're waiting for this to happen, the experiment is over. For technical reasons, when they run these experiments, they last at most maybe a minute, and it would take much longer than that for this thing to clump into a solid. We call that metastable in physics. It's not really the ground state. It's not really the thing that thermodynamically this gas wants to be, but on the timescales you're looking at it, it remains perfectly gaseous. That makes it easy to understand, comparatively easy. That's a big deal. And the other thing is you can control things very, very well. You use laser light to cool down the atoms. Well, lasers are things that you know, very well engineered. You know exactly how to build a laser. You know how to characterize it. You know what it is. Lasers cool down the atoms. Lasers hold the atoms in place. You can use magnetic fields to change how hard the atoms hit one another. We'll talk about that in a little bit. And you have lots of control over everything that goes on in there. You can set up the atoms to do whatever you want and then see what they do. That's the strategy. And now you're really starting to wonder, where did they get this guy? Because you're thinking lasers, wait a minute, lasers cool things. Lasers cool, hold on, laser cooling, because you're kind of used to the idea that lasers, you shine light on something, it heats it up, right? This is the image that comes to your mind. Maybe not this exact image, right? But you know that people use these high-powered CO2 lasers to cut steel. And you're absolutely right. Lasers carry power. They have energy. Light has energy in it. And in fact, you use that for laser cooling. So what gives? It goes back to quantum mechanics and the very careful application of light. So here's an atom. And here's light shining at the atom. And this is just a schematic thing, but light's a wave, right? So here's a wave, wah, 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 wah. And it has a wavelength. Wavelength is the distance from here to here. And this light is traveling across the room. And it's blue light. You see I've colored it blue. And as Ariel told you, you know, when you looked through these things at the light he had here, and you saw the discrete lines there, the reason for that is because the atoms will only absorb light at a certain color. And so let's say this atom is happy to absorb this blue light. So if the atom is sitting here, and the light comes along, it is just the right color light to be absorbed. The energy from the light goes into the atom, and it gives it a kick. Light is absorbed, atom starts moving. But if I have red light, here's red light. It has a longer wavelength. It's different light. This atom will not absorb it. The light will pass through, and the atom won't see it at all. The atom will only absorb the blue light in this example. Now, here's the gimmick. Suppose the atom is moving, and suppose it's moving in this direction, and suppose I shine the red light at it. If the atom were sitting still, the red light would just pass through and not be absorbed. If the atom is moving, then it sees the red light as if it were blue light, because there's a Doppler shift there, right? And so if it's moving at the right speed, it absorbs that light. So now the moving atom absorbs the light and gets a momentum kick, slows down. But if the atom's moving the other direction, this red light is even redder. And when it catches up to the atom, it just passes right through. The atom preferentially absorbs light in the direction that it's moving. And so I have a laser this way that slows down the motion in this direction, and a laser coming this way that slows down motion in this direction, and a laser this way that slows down. Okay. And so you can slow it down in all three dimensions that way. That's the idea of laser cooling. Crazy? Yes, but it works. And you can get things down to, say, microkelvin temperatures, doing things like that. There's a limit, because at some point, obviously, if you stop the atom, every once in a while, it's still going to absorb a little bit of light and get a kick. So there's a limit to that, and you play other tricks. But this is the main step. This was invented about 1987 or something like that. Okay, so that's the idea. You use light to change the motion of the atoms. You can play another trick. What I have here is, this is a very schematic picture, obviously. There's a mirror here, and I've got laser light bouncing back and forth in between. And when I do that, I get what is called a standing wave pattern. What you'll get is the light is bright here. This is the brightness of the light. This is the distance between the mirrors. The light is bright here, dim here, bright here, dim here, in some repeating pattern. And that pattern is fixed. It doesn't change in time. It's always bright here. And you put the atoms into this. The atoms, it turns out, are repelled from regions where the light is bright and attracted to regions where the light is dim. It is one of the properties of the way atoms interact with light. And so as drawn here, you can envision it if you want. If I've got this standing light wave pattern up here, there is sort of a hill here and a valley here, and the atom wants to roll from the top of the hill to the bottom of the valley. There are forces on it. And so the atoms in this scenario are moving on a landscape of hills and valleys, bumpity, 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 bump over this landscape. And here starts to be the analogy. On the one hand, we want to talk about, say, superconductors, which is an electron going bumpity, 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 bump across a bunch of atoms. The analogy is, here's an atom going bumpity, 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 bump across this landscape of light. So you're starting to draw the analogy there. If the atom's moving slowly enough, it's stuck in this valley. It doesn't have enough speed to climb that hill and get back out again. And so you can actually trap them in place, too. So there are two scenarios. They can let them run back and forth, feeling the bumpity bump, or you can hold them in place like this. And of course, both things are used. Before getting into all the applications of this, let's just set the idea of the temperature here. Here's a bunch of atoms, and they're trapped in some kind of bottle. And at room temperature, 300 Kelvin, the atoms are moving very quickly, because temperature has to do with the average speed of the atoms. How quickly are they moving? Does anybody know how quickly are the atoms moving in the air around us here? Fast. They're fast. They're less than the speed of sound, because otherwise. Approximately. But yeah, they're hundreds of meters per second. They're jet airplane speeds. Here's a dramatization of that. Do you want to see that again? Probably not. Yeah. And that's kind of where you start. Amazingly, this laser cooling starts when you create a little puff of atoms, which tend to be, rubidium is a good example. It's at this temperature. They're moving this fast. You apply the laser light to them, and they start to cool down. And you can cool them down to really cold temperatures. Here we are at the lowest temperatures, the Bose-Einstein condensate temperatures, 100 nanokelvin. They're super cold. They're moving much more slowly. He can't believe what he's seeing there. And they move very slowly. Just to set the scale, they move more like on this scale. snail scale. They, 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 they are literally moving about this fast, centimeters per second. So it's a tremendous change in the speed of the atoms. Also, I can't help but show you the kind of lab where this is actually done. Can you see that? You can get an impressionistic view. I don't do this myself. I'm a theoretical physicist. My most complicated tool is a pencil. But I have friends. Yeah, good friends. So this is from the lab of Debbie Jin, just here down the street. And you can see there's one or two things involved here. This whole thing you're looking at here sits on an optical bench, which is a big steel table, a little bit bigger than a dining room table. There's support structures. There's cables coming all over the place that bring in electricity and take out data. There fiber optic cables that bring laser light in. There's hoses that bring water in to cool off the parts that get hot here. Down here, there's a bunch of optics. For example, this is a lens. This is about the size of a $50 or so. And so the laser light comes in and it bounces around and around and around. I don't know why it goes through such a convoluted path, but then it goes into here. The atoms are in here. There's a high vacuum chamber in here. And this matters because these things you're making, these cold gases, are so incredibly delicate. They are done in super high vacuum, essentially the highest vacuum you can make in a little chamber about that big. Because if there's anything else left, any atoms that you're not specifically cooling, they will crash into your thing and heat it up and destroy it. So you've got to be at a very high vacuum. That's in here. This is a magnetic field coil. You run a current through there, and you can put a magnetic field on if that's what you want to do. Then there's other stuff. These are typically maintained by a crew of 2 or 3 graduate students and postdocs who just keep the different pieces running. These are very complicated experiments. All right, so with that, now you've got it. You've got a bunch of atoms. They're held in one of the valleys, let's say, of one of these optical potentials, or by other means. You can hold that. And at for us, a relatively hot temperature, let's say a millionth of a degree, the atoms are not yet quantum mechanical. They're still little balls bouncing around, banging off of each other. They behave perfectly classically. But when you cool them down, the rest of the way down, as far as you can go, something very different appears. What is this? You no longer see individual atoms. You see kind of a blob of something down here. What is that something? Well, Ariel told you about the Heisenberg uncertainty principle. The idea is, you remember this sort of general notion that he put on the board. The better you can constrain where something is, the less well constrained is its momentum, and vice versa. The better constrained the momentum of these atoms is, the less likely you are to know where they are. Well, that's the case here. You've cooled them down so much, their momentum is extremely well contained. It's 0. And so, apart from the fact that it's in this box somewhere, you have no idea where it is. I can't tell you where the atoms are. I can tell you the probability of finding the atom here or here or here. This blob represents the probability distribution, the wave function, the likelihood of finding an atom at a given point inside the gas here. And this thing is itself much bigger than the size of an atom. It is sort of micron-sized big. The atom, yes?
Okay, so I'm sorry, I need to clarify before you go any
Yep.
faster or farther. The probability distribution becomes smaller by the droplet. So the likelihood of them being in a particular place becomes a smaller space?
Yeah, that's an excellent point. Yeah, and we'll actually see it on the next slide. But when they are hot, they have enough kinetic energy to go further in the trap. When you cool them down, they're limited in how far they can go by low momentum. But because the momentum is low, I can't tell where they are within whatever space they have left. Yeah, that's an excellent observation. And so that's what you're seeing here. Moreover, these are bosons. Bosons are the frat boys of physics. If one of them goes down there into this blob, they all go down there into this blob. And so instead of a bunch of atoms, I have this blob of stuff. And it's 1 micron big. You cannot, usually, you cannot see these things with your naked eye. The cameras they have cannot take pictures of this. What they do is they turn off the light. They let this thing expand out. It does have some momentum. If you let it go, it will expand out till it's big enough. Then you take a picture of it on a digital camera. And here's what these pictures look like. This is by now an iconic image in physics. This appears on the cover of textbooks. This was a big deal. This was the first observation of the Bose-Einstein condensate, which was done where? Boulder, Colorado, baby. In 1995 by these guys, Cornell and Wyman. And what you're seeing here are 3 separate images. They're false color images. Look at this one, for example. Where the image is high and blue, there are lots of atoms, and where it's sort of yellow and green, there are fewer atoms, and red is just sort of background noise, no atoms at all. And at this temperature, 400 nanokelvin, which was hot for them at the time, this is a thermal gas. This is not Bose condensed. This is the gas you were talking about. It's not yet quantum mechanical. It's a bunch of atoms rattling around like this. There are plenty of hot, fast atoms. So when you expand them, they travel a long way. They go all the way to the edge here. There are plenty of atoms out here with high velocities, and somewhat more here and somewhat more here. But there's a kind of a smooth distribution, and that distribution is explained perfectly by just the classical physics of a bunch of atoms in this bucket that you're holding them in. But if you go to the lowest temperature, nothing has changed except the temperature has dropped by a factor of 8 here. And now it's completely different. Now you see a single peak right in the middle. There are no fast atoms that go off to the side here. They all have the lowest possible momentum state here. They are all in the lowest state that quantum mechanics allows them to have. In fact, this image is a pretty good direct representation of the wave function of those atoms down there. It is quantum mechanics right there in front of you on the CCD camera. And this caused a big stir because it was not known that you could actually produce this kind of thing in these experiments. It is the only other superfluid besides helium. And it took, 50, 60 years to get there. All right, well, what is this like? What is the Bose-Einstein condensate like? We'll call it BEC for short. The density of this gas is 1,000,000 times less dense than air. So it's an extremely tenuous thing, and it's really cold. And yet, it has a structure to it. It's held in this trap. It is more dense in the middle than on the periphery. That's unusual already. If I have a box of air, the density is the same all the way through. But right away, this quantum mechanical thing takes a shape, decides to have higher density in the middle. And I guess I said this before, all the atoms are in the same kind of quantum mechanical state. It's a blob of quantum stuff. It's a superfluid rather than a bunch of thermal atoms. What can you do with it? Well, it turns out lots of things. I'll just run through a few examples here. One is vortices. Is this a superfluid in the same sense that helium is a superfluid? That's a thing you'd want to go check. Or is it completely different somehow because it's a gas, not a liquid? I don't know. So here's a Bose-Einstein condensate, and it's shaped. This is a sort of perspective drawing, so it's sort of shaped like a disk. And you can imagine an experiment. In fact, people do an experiment where you poke it with a laser, and the laser pokes a hole in the condensate, and now it's a stand-in for your finger. You put the laser in there, and you can do this and stir up the condensate like that, you see? And you stir it up and you ask what happens. Do you get vortices? Are they persistent like they are in superfluid helium? And the answer is yes. I picked this up because it's a pretty picture from the MIT group. Here are 4 images of 4 different condensates. Here they haven't stirred it at all. They get this typical picture where it's high density in the middle and low density at the edges. And then if they stir it up to different degrees, look at this one, for example. Sure enough, they get holes in it. They get these vortices, which is basically superfluid swirling around these little holes there. So now try to take this in. Here's a gas, and the gas is 1,000,000 times less dense than air. There's hardly anything there at all, and yet it has holes in it. Right? It has structure. This is amazing. The quantum mechanics supports the structure, holds it up. And again, for the minute or so that they can hold on to these atoms, these are perfectly persistent things. The BEC is a superfluid in that sense. Yes, question?
What element are these?
This is, in this picture, it's sodium.
Okay, so they are just different ones that we're going to
Yeah. So there are technical reasons why the elements in the first column of the periodic table are best for laser cooling. So a lot of the early experiments were on sodium, potassium, rubidium. Cesium is a big one these days. This particular image is in sodium.
And it may be worth mentioning that if you kind of add up all the spins in the atom, they can add up to an integer spin. Is that right?
Exactly, yeah.
So they can, once they're cold enough, even though the particles are made up of fermions, the whole atom can act like a boson.
Yeah, consider lithium, because that's the one I know the numbers for. Lithium has 7 electrons in it, 7 protons, and some even number of neutrons, 6, 8, whatever it is. Whatever it is. But yeah, he's exactly right. The atoms are made of fermions, of spin 1/2 objects. But if they add up to be a total object that has an integer spin, they count as bosons, and they can do Bose-Einstein condensation. All right, so that's one thing. There's this tenuous quantum mechanical gas with all this structure. And by the way, you can do further experiments on this. These little vortices, it turns out, move around, and they can exert forces on each other, and there's a whole story of how they behave, which I won't go into here. But here's another part of the story. If you have, not a single trap, but sort of this standing wave where the atoms are running over the hills and the valleys, then you ask yourself, and remember, this is the question we're getting to, what is the complex motion of lots of atoms acting together? So let's put a lot of atoms in this. And what the atoms are doing are affected by, well, running over this lattice, bumpity, 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 bump, and by running into another atom, because atoms hit other atoms, and that matters. That obviously changes their motion when they hit and bounce off of each other. And if you build a gadget like this, you tend to do it in 2 dimensions. So there's a laser going back and forth this way that makes bumpity, bumpity, bump, and a laser going back and forth this way that makes bumpity, bumpity, bump. And so the landscape is this nice sort of periodic 2-dimensional array of hills and valleys. And I populate it with atoms. And depending on how bright the light is, the hills can be very shallow, and the atoms can easily move back and forth and move around, run into each other, and congregate and do whatever it is that atoms are going to do. And that's one of the questions, what will the atoms do? Or if I turn the light up much brighter, I can make the hills, the valleys very deep, and I can make it so that at a certain temperature, the atoms get locked away in these. And what they tend to do is accurately pictured here. They tend to land one per site. That's something the atoms decide to do on their own. It's one of those emergent properties of having lots of atoms. That's the kind of thing you can probe with this. And here's, whoops, what have I done? Here's how it looks in practice. This is from the Greiner group at Harvard. There are 2 very different cases. If the lattice is high and the atoms are sort of one per site, I imagine there's an atom sitting in this valley, and I expand it, well, I'm going to get a result that looks like one atom expanded. And the next one is going to look like one atom expanded. They're independent of each other. And what I get is kind of the sum of everything, sort of a featureless thing, lots of atoms with low velocity, fewer atoms with high velocity, not terribly interesting. If I go to the other case, the barriers are low, the atoms are free to move around, although they're moving around in bumpity, bumpity, bumpity. They're running into each other. I get something more like this, much more fascinating. A lot of the atoms have no momentum. They have not expanded out. But in the time of expansion, some of them have moved from here to here, but not here, not here. They had some velocity there, but they don't have half that velocity. They can move in this direction, but they don't have that velocity. They don't have that velocity. They don't have this velocity in between very much. The atoms have somehow arranged themselves to do this, to select velocity classes for themselves and go about their business. This is the kind of emergent behavior that you can study with these things. Just bizarro stuff. There is one last piece of the puzzle, and that's interactions. We talk about the electrons moving through the superconductor, and electrons are electrically charged. They repel each other. Atoms are electrically neutral. And so to talk about them interacting, what you mean is they run into each other. And in classical physics, you look at this and you say, well, here's an atom and it's this big, and here's an atom and it's this big. And if they happen to be aimed pretty much at each other, they would hit, bonk. And if they're aimed, if they're aimed not quite at each other, they can fly right by each other. And it's a very hard criterion. They hit or they don't. In quantum mechanics, it's very different because atoms are not particles. They are waves in quantum mechanics. And waves diffract and interfere, right? You're becoming a physicist now. Right? And when things interfere, things get, collisions and interactions get much more interesting. Here's an example, just an optical example. Here's some kind of ball, and here's light shining on it. And you might say, well, if I'm standing back here, I would see pretty much no light coming through because there's this ball in the way, and it would block the light. But no, there's interference, there's diffraction, and the diffraction makes the light go out this way and this way. So standing back here, I would have guessed that effectively the light is scattering from a much bigger object because I see something much bigger back here. Diffraction can make the atoms, which are waves, look bigger than they are, than the actual size of the atoms. And we can put this to use. There's a thing that we do in this field. I'm sorry to show actual data here, but you know, I couldn't think of a nice cartoon for this. But the point is, the atoms themselves are, of course, small objects. Something like 1/10 of a nanometer is the diameter of an atom, give or take. And so roughly speaking, without quantum mechanics, they'd have to come within that scale of each other to act like they've hit. But because of diffraction, they can act as if they're much bigger. And the really amazing thing is, this is a stunning thing, that the atoms behave like little bar magnets, and you can tweak little bar magnets with a magnetic field in the laboratory. And so now you have two atoms, which are waves, come in, scatter, diffract, act as if they were a certain size. And now I go to a different magnetic field, you see. The atoms are slightly different from what they were before. They come in, they are waves, they diffract off of each other, they scatter off in a different way. The effective size of the atoms due to diffraction is something you can control with a magnetic field. Whoa. Right? And, you know, for now, you're going to kind of have to take my word for it because it's a fairly complicated thing. But here's the data, right? So this is magnetic field on this axis. And the point is, this is an interference because waves interfere. And they can interfere constructively and make something bigger than it would have been. They can interfere destructively and make the amplitude smaller than it would have been. And so at a field of 200 Gauss, this is, and I apologize, I've switched atoms on you, but it doesn't really matter. So in this atom at 200 Gauss, the atoms behave as if they're 50 nanometers across, not 1/10 of a nanometer across. They hit each other, bang, really hard. That's a large interaction under terms, a large repulsion. If I have an atom sitting at the bottom of one of these valleys and another atom's trying to come in and it sees a 50 nanometer atom already sitting there, it's going to say, no thank you, I'll come back later. Right? But if I change the magnetic field to just 210 Gauss, suddenly they behave as if they're half a nanometer. Now it's a comparatively small atom at this valley, and if another atom comes along, it's a little more inviting, you see. And so I can control how the atoms try to arrange themselves in the valleys of this potential, how they interact with one another. That's under our control. So let me sort of wrap up with the bringing everything together. We want to understand complicated things like superconductors, which have, you know, this incredibly complicated array of atoms. A difficult to understand lattice of atoms. Just that first step, understanding where these atoms are, is a big deal. If I do the analog in the cold atom system, this lattice I know exactly. If I know the wavelength of the light, I know the spacing between the valleys here. No question about it. If I know how bright the light is, I know how tall the valleys are, the mountains are relative to the valleys. I know everything about this perfectly. So that makes this easier than that to deal with. In a real material that I mix up in the lab, this, did you see what happened there? Instead of being nicely aligned like that, oh no, it's broken there just because of the way it was put together in this, you know, I don't know what they do. I envision a crucible somehow, but I don't really know how this works. But there can be imperfections that you can't characterize very well. This one, no imperfections. It's a perfect lattice. Unless, you know, if I decide what I want to study are imperfections, I can make the laser go and build in imperfections if I want. People do that. So I have complete control over that. I have electrons moving through. The electrons have to talk to each other via electrostatic forces. Those forces depend on how far away they are and what's between them and all this kind of yuck. The interactions between atoms, I control the magnetic field in the way I told you about. I set that. There's no ambiguity there. So I know everything about this. Here, you mix a little bit of this, a little bit of this, and a little bit of this, and you stir it up, and you bake it, and you attach electrodes, and you ask yourself, when does it superconduct? And you just don't know till the end. Here, you can design anything you can dream up. There are millions, dozens of proposals where people say, gee, we have so much control over this. Why don't you build this artificial material? Why don't you do this? Why don't you set this up? And the proposals get more and more far-fetched, and people are trying to design things that are crazier than superconductors. And but you know, the imagination is your limit there. You propose something, and it sounds almost plausible for somebody to do. And maybe the point is, it is almost plausible. So I showed you the result of the one experiment where, you know, the things in the lattice gave you this strange structure. It's happening now. The rest are being developed now, and in the next 5 or 10 years, we're going to see lots of weird engineered structures coming out of this and learn a lot about many-body physics. So that summarizes this. Just to summarize what I'm talking about, there are custom-built materials made of atoms and light that are controlled by things like magnetic fields, but also more light or microwaves. There's all kinds of things you can put in there. You can engineer matter of this sort now. It is engineered as perfect as you need it to be. It's controllable and therefore in principle understandable. And the big goal is it will help us understand this problem of quantum mechanical complexity. What do a bunch of atoms do when they're given a lot that they can do, or something like that. And so let me just stop here and thank you for your attention.
So what kind of data is generated by these kinds of experiments? Like terabytes or whatever bytes, petabytes? No, it's not like the experiments that really generate lots of data are particle accelerators, where they throw protons at each other, and 1 trillion times nothing interesting happens, but you don't know which of the 1 trillionth time. So you collect this enormous amount of data. Here you do it once and you get a result and you see it. And you do it because you want better signal to noise, but it's not a massive amount of data. But it is, so it's not a massive amount, but in what kind of format? So that if we were trying to preserve that data for somebody else, would it be just a plain old spreadsheet? Would it be, what would it be?
It's a lot of digital pictures, really.
Yeah, it's really pictures just like this. So they'll have those files, and I don't do it myself, so I don't even know what format they store it in. But I can guarantee you walk into these labs and they've got, they have computers dedicated to storing these images and backups of these images. They have a shelf this long of laboratory notebooks where they've printed out pictures of these things. It's not an overwhelming amount of data, and they have it all.
Yeah.
How did Wineland's work fit in with this? Because it seems like some of it, what I read, is
this is
the new Nobel Prize.
This is last year's Nobel Prize winner, Dave Wineland, who, there's an interesting story. So these are all neutral atoms. And when Wineland got into the business, he started working in ions. It's because back in the day, you realize an ion, because it has an electrical charge, you push around with electric fields, and those are really big forces, and it's very easy to slow an ion down to more or less rest, whereas with lasers, it takes a lot more doing. So in fact, the ions were cooled first. It was Dave Wineland, the story goes, who first used lasers to help that out. The invention of laser cooling is arguably Dave Wineland's, and he was skipped over for that particular Nobel Prize, not that we're bitter, right? Because he got his later on. And he continued to work with ions, and you can do spectacular things with ions, especially, these are, I probably didn't say it, but in these gases, these are collections of tens of thousands of atoms all at once, and you have no hope of seeing them. If you have ions and you hold them in a trap, you can put like 10 of them there, and you can see them. You can see a row of 10 ions just hanging in your vacuum chamber. And there's a whole different set of physics that you think about doing when you can look at individual ions than when you see the whole collection of stuff. Yes?
Question for both of you. Do you use library resources or librarians on your research?
Yeah, so I mean, physics has changed a lot, right? I mean, I think there was a time when you had to, and now some of the journals are incredible. I mean, I think it's Physical Review Letters, you can look at any PDF back to 1898, I think, when they started publishing them. Yeah. So it's quite a bit easier to find, and the physics community is very good about its resources, right, and being able to search its resources. So I have to say, in my graduate career, you're just a little older than me, but a scotch.
What's that?
you may remember a card catalog, and but
Librarians set those databases up to make them easy for you.
Right. I'm saying my human physical contact with a librarian in my graduate career was zero.
But it's a good point. You need an article, and you don't even know what article you need, and you just Google it, and it's there. And our library here has access to lots and lots of journals, and a few keystrokes, you've got the article.
So I would say, yes, our library system at the University of Colorado is extremely well set up for us.
Yeah.
And so I think in a meta sense, I have dealt with librarians, but I've never talked to one for the purposes of finding a particular article.
You know, and to add to that, there was a time also when if you taught a class, you would have material on reserve at the library, you know, an extra textbook or something like that. And certainly I interacted with librarians, and even that is, I hate to say it, going away. You put your own materials in PDF files and link to them.
I'm going to throw a librarian question at you now, back in my own. So undergraduates, do they need to access original articles, or are you guys reliant on your own knowledge and hopefully the storytelling that you're giving to us, you're giving to them to keep them excited as they work through the math? Do you use textbooks and your own knowledge, or do you have them go out and look at reserve articles? So.
You mean in classes?
Yeah, in undergraduate classes especially.
In a lot of, I have to say, textbooks are really good these days and have most of what you need in them. In my own teaching, maybe once a semester, twice a semester, I'll say, hey, there's this great article, you guys got to go look this up.
Advanced undergrads in physics are often encouraged, and it's part of the class in something like our electricity and magnetism classes. They have to look at articles. Look at current articles, and definitely in your graduate career, I mean, it's huge, right? I mean, that's what you spend a significant portion of your time doing, is looking through the literature. But less so at the undergraduate level, unless you get to the advanced level, I'd say.
So the undergraduate program, correct me if I'm wrong, is basically lecture and textbook driven?
Mainly lecture and textbook driven. For the lower level undergraduates, as you move more towards that graduate level, you know, this upper division, quantum mechanics and electricity and magnetism classes, there is a component usually that's involved with looking at a research paper, understanding it, and current research papers, not just some, you know, looking at something from the 1950s, really looking at more current research.
There is, if you're in graduate school here at our department, you're required to go through the comprehensive exam. And a part of that is produce a short review article on some contemporary topic. And that is expected to be really a literature survey. And you have to look around and synthesize a lot of material for that. That is one of our requirements. Yes?
Let me flip her question in a way that might make you a little more comfortable. How do you guys find out about what other people are doing? Are you reading articles? Is it RSS feeds? Is it emails? Is it conferences? Or is it some combination of all of those?
I think the answer is yes. To everything you said. I mean, it depends on, when I worked as an experimental physicist, you're doing literature sources, you're going to conferences, you're talking to colleagues. People can sign up for these virtual journals these days where it conglomerates different articles from different journals. So I think, what's interesting, I think what was great probably when you were in the days of Faraday, you're like, I move this magnet towards a coil of wire and I see an electromagnetic force.
Do tell, old boy.
Science was easy, right? There were people wrote letters to each other. So, but now the amount of just sheer information out there is huge, right? So sometimes I think the challenge when I was a graduate student is you look at certain topics and there's, articles like John's sitting out there, which are not very well cited, that it can be a deep search if you're really trying to find one specific topic. There are times when I did have to go to the library and actually physically find something, but that was a rare occurrence. I was looking for an article about water jets and Rayleigh instabilities, and the only place I could find it was in the engineering library in this textbook. There was no PDF of it. But a lot of times it's you read an article, and if people are good in the community about citing, you kind of go further down the hole by looking at cites. Often happens. So things being cited well in an article is hugely important. So,
but can I add to that? There's also this ePrint archive, which is a big deal these days. And if you want to know what's going on right now, you don't wait till it comes out in the journal. You slavishly check your subject matter on the archive every day, and you find out who's doing what. I think that's one of the big deals now.
Yeah. Well, and I'll just say, so I talk about forward citing a lot when I do consultations with grad students and faculty, but I also caution them, don't believe that an article is bad because it hasn't been cited It's just not in the right place at the right time.
Absolutely.
But certainly if it has been cited, it is generating a conversation. There is stuff going on with it. Thank you.
What kind of training do the beginning graduate students get to participate in that? Like that kind of research, the literature survey. Do you guys, is that just like they had a great...
Grad school's not about training. Grad school's getting thrown into a fire, you know, and you talk to other graduate students. People help you along the way. Grad school is amazingly lacking in formal training of what you really need, like social skills. And, there's so many things, plumbing, you know, if you're an experimental physicist, there's so many things you learn by doing. And there's really your classes that you take, and that is changing a little bit, but your classes that you take are very much the same as they were 100 years ago, I think, in many respects. You know, electricity and magnetism has been using the same book for 50, 60 years, and you're trained in a very specific type of formalism, but these meta skills, you know, how to do literature searches, how to find the articles you're learning from, you learn from your advisors, you learn from your fellow graduate students. I never took a class on that. I don't know if you did.
No, there's no such thing.
Yeah.
No, I would say
it would be useful. Don't get me wrong.
But especially at Gilla, there's a very collegial atmosphere. Yeah. All the students know each other, and they teach each other the tricks of the trade, and that's really how it's passed down.
So, how do you communicate with your colleagues around the world? I mean, when you engage in collaborative research, how do you communicate, and what things do you need from your respective college or university and the larger infrastructure to help you do that kind of communication and make sure that you're keeping the right kinds of information, everything else pulled together so that you can function?
I use email a lot because if you're talking to your collaborator, you have some carefully reasoned argument you want to make. So you write a little document, you put figures in, you put data in, and you send that off so that it's just like writing letters 100 years ago. And then your collaborator can sit down and thoughtfully go through it. And there's a lot of that goes on. And then once in a while you have a Skype chat. And you really argue about it.
Do you use citation managers or anything and have set up groups so you can share stuff? Like EndNote or Zotero or...
We use EndNote, yeah.
Okay.
And again, I guess, is any of that back and forth communication important to keep or retain in any way? Or do you ever need to refer back to it?
Every scientist I know saves every single email they've ever sent. I mean, really.
Yeah.
I mean, because it's such an important record, and they back it up. And you know, Gilla is a wonderful place to work. When I'm now straight in the physics department, but Gilla has taken lots of time and effort to make great backup systems, and it's easy. They have servers where you can just drop what you need on the servers, and they're very good about that because they understand it's such a need. In fact, they have their own internal system. You know, they don't rely on the rest of the university necessarily because our data is so important.
So, among physicists, are you
Wait.
willing to share data?
With whom?
It depends.
It depends.
It depends. You have, John could probably answer this more, but I worked in a group that was highly competitive in terms of the field we were in, and you don't usually share the data until it's published, because funding is tight, and people get scooped. You can work on something for 2 years, and someone comes out with an article that gets in front of you, and it really gets to the result you were chasing. So.
These guys made the Bose-Einstein condensate, and they knew Wolfgang Ketterle was doing that at MIT, and they were damn well going to beat Wolfgang Ketterle to it. They did not.
When you do your research, do you ever find that there are gems of information hidden in archives, like scientists' special collections that aren't published or digitized yet? Have you found that yet in any of your research?
Not so that aren't published or that aren't PDF'd.
No, I mean like their notes. They're the way that they published a book, but the papers before they published the book are in an archive, and maybe there are some things that they didn't come
There
out
are
with
some
yet.
articles definitely in the field I worked in as a graduate student that were very classic to what we did, but it was a small, I worked on this thing with hollow waveguides that there was a classic paper from Bell Labs that was not digitized. You had to go find it And no one had, I mean, someone may have by now, but that was one of those that you had to read, but you had to have the print version because it was just very difficult to get. It was in this sort of obscure journal. So yes, there are definitely things like that out there. Certainly when I was a graduate student.
It's changing. Yeah. There are articles that have been hard to find, and you actually have to track them down and get the. But that happens to me less and less these days.
So with all those emails that everybody keeps, would there be value to the physics community for being able to share that kind of stuff, or is that the same with the? Because you've got yours, and he's got his, and he might have something that would be useful to you, or is that with the competitive thing?
Let me tell you something about how real science goes down. A lot of things that get written in emails you don't want out there. I mean, really, because scientists are snippy, scientists are people. There's a whole sociological side of science that I think no scientist I know would ever want their entire email collection out in public, because people say things that I think you wouldn't want to be seen in public. Because every time there's controversial science, people argue about it. Oh, that person doesn't know what they're doing. That person's wrong on this. And that stuff's, you may remember there was this scandal about climate change, right, that came out. And any scientist's like, well, that all seems normal, what they're saying about each other. But to everyone else, there's a big scandal because they think science is this clean thing. And it's not. When it really goes down, there's a lot of back and forth. In the textbook at the end, when we've hashed it all out, it's clean. But the process of doing it is not clean. So I cannot see, I don't know if you agree with that or not, but I would say that no scientist that I know would want all of their emails public.
Some of my colleagues, one of my colleagues has worked a lot on the great literature, particularly in science, and for the last 20 years she's worked on that concept of how to get stuff out of people's offices so it gets to be useful. It's not about your email, but it's the useful stuff. When people retire and it ends up, and now it's digital. Instead of the stuff that goes through the dumpster, it's just going to get.
Could you repeat that?
GILA is a work group, and you have support systems, but there are thousands of other people who are just in their offices with their server, and then when they leave the university, their hard drive goes in the closet. So those are interesting questions for librarians. So we're always interested. We're interested to find out what you guys hear from your colleagues right now about someone who retired last year. You see where that data can go, or does some of that show up at GILA? Somebody is winding down their work.
I think that's why you have graduate students. No, really. I mean, because it's interesting. So I had a physics professor, when I asked him, what book did you use for electricity and magnetism? And he said, he was Swiss. He said, there was no book. Someone wrote, he gave very good lectures. Someone wrote it down, and eventually it was turned into a book. That was Wolfgang Pauli. So he took his class from Wolfgang Pauli. I mean, there's an oral tradition to physics, right? So you sometimes get information from your advisor. Oh, you should go look at this article. Here's this neat little trick, and it gets passed down to the graduate students, and it's that cultural knowledge of physics. So I think any good professor who's had graduate students, that knowledge base, some of those things that aren't written down are in people's heads.
Well, can I add to that? So, physicists these days are publish happy. And if we have anything that we think is at all worthwhile, we're going to put it out there. And for the sort of things that get passed down, I would say that's getting more formalized these years. Somebody writes a PhD thesis, one thing you encourage them to do is to write down enough details that the next graduate student can see it. And so now that's there. That is published. And I would say in that sense it's getting less and less like it's word of mouth.
But I've hung out with Jan Hall, who's a Nobel Prize winner.
Right.
And his office looks the kind you're talking about, where if you open the door, like papers just fall over. And you get gems of wisdom by talking to him that then do get written down in theses, I think. Yeah.
Question. I worked for a chemical division of a private corporation for a few years as an information scientist. And we had a person who was developing a resin. He put months in, tons of money in, and by the time he was done, turned out there was a pre-existing patent that was owned by another company, and he had never thought to go to the library, and he got so blasted for that. Do you all ever have situations where your students say, why didn't you all teach us how to do a patent search? Or, there's some things that scientists need to know how to do that they don't always learn in the classroom, that they will learn from big companies. Plus I worked for JPL, my first job was with JPL. And that's why they were there, was so that somebody would come in and say, oh, this is how you find this. Don't you have those situations where you have to use certain sources? do you teach your students that?
I mean, certainly we, right. If we're, because this happens a lot where you think you have some great new idea.
Yeah.
And the first thing you have to do is go see if anyone else has that idea.
Yeah.
I think that's just part of the culture that it's known to do that. I was never formally taught that. I mean, but you knew that your advisor, part of your advisor's job is to have a feel for the community and what's going on. But anytime you came to something that
he had graduated and was in corporation, and he'd never been taught this is what their function is, and
I've certainly done patent searches.
Yeah.
But I found that a very interesting analogy. And I think in academic physics it might be a little different because everybody who has an idea wants to get credit for that idea, and the way they do it is to publish it in a big prominent journal, and the rest of us all know about it. And so in my field, I know all the people in my field. I know the ones to watch, and I go to the archive every week and say, what has Duncan Odell done this week? And can we beat him to it? And so I think we have a real high level of awareness of what's going on in the things we're working on.
Okay, so you don't do a lot of things like that.
And so it becomes, so it's part of the culture. My students check the archive every week because they know to.
It is definitely in physics. It is culturally embedded because, and I think partially it is because of the funding culture, right? That because it's tight, you have to go after new ideas that you can publish. So it's really embedded in there that it's got to be original, and how do you show that it's original, and making sure that you're going after something that's original.
What's more interesting is you come up with an idea, and you're developing it, and somehow you find out that 30 years ago, somebody did that idea. And that's not always a straight route to find that.
Yeah. So I think just one more question, and then we're going to have to get out of here.
I want to ask a non-primary research question, because I'm a book publisher, so looking at Devergen's kitchen table cooling machine, where do physicists go for learning design, methods, instrumentation? As soon as you didn't build it on your kitchen table, how do you efficiently learn and teach things like building instrumentation design to make your experiments work?
That's down your alley.
So I worked for 4 years in the Jill Instrument Shop. I did an apprenticeship in scientific instrument making. I happen to love to work with my hands. But these skills that you're talking about, sometimes it's chewing gum and duct tape, and there's really this, if you ever get the chance, go to Jill and ask just to peek in one of these labs. It's amazing what people do. And it's insane at the same time. And there is a lot of knowledge and tricks that you have to do hands-on learning. It's on-the-job learning. There's no training manual. There is no class you can take. You have to do it to understand how to align certain kinds of optical components, to understand, how you wire up certain kinds of photodiodes or using certain designs. It's not written down anywhere, and there is no way to write it down. There are little tricks of the trade that you just have to learn. You can write down some of them, but you can't write down all of them. And I think the analogy would be there's chicken egg sexers, right? Or chicken sexers, right? That the way they teach someone is you stand next to someone who's the chicken sexer, and they're saying, that one's female, that one's male, that one's female. And you eventually pick up on some things, and there's no manual you can write down. This is the way they literally teach people how to check the sex of chickens, right? So there's some of that goes on in physics that you just have to be in there, in experimental physics, in there doing it. And at places like Jilla, we have training classes for the electronic shop, training classes for the instrument shop, but that only takes you so far. Learning how to make a mechanical design that doesn't vibrate much. It's just some of it's art. There really isn't a manual for some of it. So.
Okay, well, let's thank our speakers.